23 पॉइंट्स का पॉलिनोमियल इंटरपोलेट करा था, फिर उसका डोमेन एक्सटेंड करा था, इवैल्यूएट करके कमिट करा था. But there's a slight problem. So we wanted to evaluate the polynomial in approximately 8 into 1024 points. And the degree of the polynomial is 1023. So can anybody tell me the time complexity of this? So I have a polynomial f of x. The degree is n, and I want to evaluate it on m points. What is the time complexity of this? Okay, what is the time complexity of evaluating this polynomial on one point?
N.
O of n, right? Yeah. So then for m points, it's just O of mn. Pretty bad, but it's quadratic time complexity. So we want to reduce this, क्योंकि अगर reduce नहीं करा तो there's no point of this whole proof system anyway. It's not scalable. So how do we do that? So there is a O of n log n method of doing this. So let's say you have a polynomial f of x. Let me just. This is the pseudocode. So the polynomial is a0 plus a1x plus a2x squared, so on, up till an xn. And what I'll do first is I'll divide this polynomial into odd and even parts. So this is just a0 plus a2x squared dot 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 plus x into a1 plus a3 x squared, so on. So I'll call this polynomial even of x squared, and I'll call this polynomial odd of x squared. Now what we can do is we want to evaluate this polynomial on m points. But if we strategically choose these m points such that they have some sort of property, we can use this property to make this evaluation n log n. So what I'll choose these m points to be the mth roots of unity for now. And later you'll see like the property that the mth roots of unity have is very similar to the property of the group, the cyclic group. And this is what allows us to do this computation in n log n. So I want to compute f of x on 1 omega omega squared up till omega m raised to minus 1. I'm going to assume that I can do this. So I'm going to do an induction type of method on this. I'm going to assume that for this polynomial, e of x squared, I can compute the values of 1 omega squared omega raised to 4, so on up till omega raised to m minus 1 by 2 in n log n time. So let's say I've computed e of 1 omega squared omega raised to 4 and so on. And let's say I can do the same for this odd polynomial as well. So for this odd polynomial, I know the values of O of 1, O of omega squared, so on. If I do know these two evaluations of the even and odd polynomial, can I find out the evaluation of f of x at 1 to omega raised to m minus 1? The answer is yes. Like you can clearly see that f of omega raised to I is just equal to e of omega raised to 2i plus omega raised to I into odd of omega raised to 2i. And I already know omega raised to 2i because that's my induction hypothesis. And I know omega raised to I. So I have made calculation of f of omega raised to I an O of 1 operation. Okay, so this was slightly dense. Does anybody have any questions? Anything you didn't understand?
Take this equation like omega square omega power 4 till omega m minus 1 by 2.
Yeah, so I want to evaluate this polynomial at omega raised to I, right? So omega raised to I is one of the mth roots of unity, right? For that, I need to evaluate on the even polynomial at omega raised to 2I, right? Do you agree that omega raised to 2I is m by 2th, m divided by its 2 root of unity? So omega raised to 2I is m by 2th root of unity. Do you agree with this? Okay. So, and omega raised to 2I is of this form.
Remember 2 times m minus 1. That.
Sorry. You're right. Should be 2. But what you see is that 2 into m minus 1 would overlap with one of these elements. So initially, if you have m elements, you would have m by 2. So it would be something like m minus 1 by 2 ka ceiling. Right? Okay.
But initially, if you have m minus 1 element, then
So if you have m elements initially, because you have m roots of unity. Now you want m by 2 roots of unity. So you would have m by 2 elements. So
shouldn't be the floor of m just m minus 1.
yeah, so okay. Essentially, we will assume right now that m is of this form.
Okay.
And so then we would have 2 raised to I minus 1 elements later, right, after the m by 2 step. So that would be, so which is just equal to 2 raised to I minus 1 by 2 ka ceiling. Agreed? Sure. Okay. Let me try to explain this again. Okay.
You're reducing the complexity from n into m to n into log m.
M into log n.
M into log n.
Yeah. Every time I'm reducing the degree of a polynomial by 2. So this even polynomial has degree n by 2. This odd at max, this odd polynomial would also have degree n by 2. And if my time complexity is something like n log m, then each of these would have time complexity n by 2 log m by 2. Yeah.
Is it not m to power I minus 1 by 2? Like,
Sorry?
they're half of that number.
Yeah. Half of m, right? So okay, so initially I want to evaluate this polynomial on the m roots of unity, right? When I do this evaluation, I want to evaluate e at x squared. If x is a mth root of unity, x squared is a m by 2th root of unity, right? So I would have to evaluate this even polynomial at 2 raised to I minus 1 elements. Agreed? Yeah. Anything that doesn't make sense?
Still here it is okay.
Yeah. Okay. So essentially, I'm assuming that for any polynomial of degree less than n, using my induction hypothesis, I'm able to evaluate m roots of unity in n log m. That's my induction hypothesis. And then once I can do this for E and O, I can now evaluate f of x in just n steps. Still feel like a lot of you have not understood this. But I'll get back to this at the end once again. It's not a very easy concept. But yeah, let's review this again at the end. Okay. So this was a bit of a digression. I just wanted to show that the prover can compute its sort of commitment in O of n log n time. And that is what we want, because otherwise it would not be scalable. Okay. So now we've gotten to the point where we need to prove that CP is a polynomial. And we need to also show, okay, so CP is a polynomial, but we want to show that CP is close to a polynomial of low degree. Can anybody tell me where this low degree statement comes from? Why would it be low degree? Low degree with respect to what?
Instead of the whole domain, you are extending only.
Right. So CP initially was a polynomial of 1023 degree. Then we extended the domain 8 times.
But
So
still the
degree remains the same. So it's low degree with respect to the domain. And what do I mean by close? So close essentially means that if I have some function f which goes from D to f and a polynomial p, then the distance is the number of points such that fx is not equal to p of x. And we want this distance to be very less.
CP. What is CP?
CP, remember the polynomial that, yeah. Okay, just where do we get these alpha i's from? Does anybody know? So this is alpha i's are randomly generated by the verifier and given to the prover. Okay. So that's distance, and we want to show that this polynomial CP of x is close to a polynomial of low degree. So we're going to use close to. So yeah, sure. So close to means it is for a very less number of points, it is not equal to that polynomial. Now, okay, so for now, you can assume that it means equal to. This close to factor comes from the fact that we're doing something called FRI, which I will show later. And FRI gives us a guarantee of closeness. It does not give us a guarantee of complete equalness. Okay. So FRI, fast read, blah, blah, blah. We want to show that CP of x is close to a low degree polynomial. So how do we do this? Okay. So here's what the protocol does. Okay, the verifier will give a random beta to the prover. The prover will apply this FRI protocol, and after the FRI protocol is applied, the polynomial CP of x's degree gets reduced by 2. Then the prover will commit this new polynomial, and then this whole steps will be repeated again and again until the polynomial is of very less degree, such that the verifier can actually verify it in less time. So this is what I wanted to show. Can somebody tell me why it's not feasible? So I have this polynomial CP of x, right? Have this evaluated this polynomial at some 8k points, and I have generated some Merkle tree from it. I want to prove that this is actually a polynomial of low degree. How is like one way to do this without this FRI protocol? What is just one very simple way that the prover can convince to the verifier that this is actually a polynomial of low degree?
Try to construct a polynomial.
Yeah, or the prover could just send these 8k elements to the verifier. And then the verifier would interpolate by himself, determine that it's a degree of k, which is less. So we've verified the proof. But this isn't very efficient, right? We want the verifier to be in log n time, some polylog n time. So we don't want to do this. Instead, what we want to do is we want to divide this whole chunk by 2, so on and so forth, until we get a small enough chunk that now, okay, it's now the verifier can actually prove this in some log n time. So what we do is this verifier will give some beta naught to the prover. The prover will take this polynomial, do something with beta naught and the polynomial. I'll clarify what is done. This whole polynomial would be reduced to 4k elements, and if this was degree n, this is now degree n by 2. We'll construct a Merkle tree and send back the root. Okay. And then again the verify will give another b1. Now for this new polynomial, it will do the same operation. We'll get n by 4 degree 2k points, construct a Merkle tree and send the root. Okay.
This is a beta being used.
Yeah, I'll explain that. So beta is used in the FRI operator, which is used to divide the polynomial into.
And what's the point of sending the Merkle roots again and again?
Yeah, so that we'll see in the verification step. So right now the verify is just sending some random data over, right? And prover is sending some commitments. But the verifier doesn't really have a way to just verify these commitments as of yet. And so
It's supposed to be non-interactive, right?
yeah, so you will see at the end how it becomes non-interactive.
Beta
Yeah.
is some random number.
Beta is some random number, yeah. Okay. So what is the FRI protocol exactly? And you'll find that the FRI protocol is eerily similar to FFT. Okay, so what happens? We have this polynomial P0 of x. Again, like in fast Fourier transform, we'll divide it into two parts, one with the even powers, one with the odd powers. So we'll get g of x squared and h of x squared. So the original polynomial is p of x is just g of x squared, which is the even part, plus x times h of x squared, which is the odd part. And now we can get a new function, which is p1 of y, which is g of y plus beta h of y. Can somebody tell me what is the degree of p1y? So if the degree of p of x is n, is 5, sorry. So what is the degree of p1 of y?
N by 2. Scaling of n by 2.
So it would be 2, right? Because right. So yeah, so right. So it is 2. The degree of p1 of y is 2. You
P1
understand?
is the polynomial generated after
Like reduce.
Right. P1 is this polynomial. Okay. So we've generated P1. The domain has also been reduced by 2. How has the domain been reduced by 2? Can somebody tell me? Any idea why?
We have removed all the odd
Points
components.
are squared, so
Right. Has something to do with squaring.
the previously the extended domain was a cyclic group, so
Mhm.
squaring effectively halves and gives the every other element.
Exactly. So because we are squaring, written this somewhere. Yeah. So because we are squaring, if you see here, any element d that remains in domain d1, only if there is a element d dash in the original domain such that d dash squared is equal to d. And you'll have exactly half of these elements every time. So every time your domain is also getting reduced by 2, your degree is also being reduced by 2. Okay. So we're reducing the polynomial, so on and so forth, but it probably doesn't make sense why we're doing this or why this even helps. Right? How is this even proving security? So that is the next part of this. 1 second. Okay. Yeah. So why are we doing this, right? So we had a trace initially, then we created the polynomial Cp of x, then we applied the FRI operator again and again, and now we're left with a very small polynomial, very small or even constant polynomial. Okay. Now we want to have the verifier actually be able to prove, have the prover actually be able to prove to the verifier that all of these computations are correct and Cp of x is actually a polynomial, right? Because we want to show Cp of x as a polynomial, that's our end goal. Okay. So here's what the verifier will do. So verifier will randomly send some element x to the prover. The prover will send element f of x, fg of x, and fg squared of x. Fg x squared, sorry. Slightly wrong. Okay. So the prover will send these elements to the verifier. From these three elements, the verifier can calculate what Cp0 of x is. So Cp0 of x is the first polynomial Cp of x. Now, the verifier, so you can see through here why the verifier using f of x, f of g of x, and f of g squared of x can compute Cp0 of x. Then the prover will send Cp0 of minus x, and then using Cp0 of x and Cp0 of minus x, the verifier can compute Cp1 of x squared. And here is why the verifier can compute Cp1 of minus x squared. Cp1 of x squared, sorry. Yeah, so the reason is, initially Cpi of x is g of x squared plus x h of x squared, right? Then Cpi of minus x, just create a minus x, so you get g of x squared minus x of h of x squared. So essentially we're able to represent g of x squared and h of x squared using Cpi of x and Cpi of minus x. So Cpi plus 1 of x squared, which was represented in just g of x squared plus beta of h of x squared, beta hx squared, can be represented in terms of Cpi of x and Cpi of minus x. So you can forget about the calculations, but essentially there is some function g that takes Cpi of x, Cpi of minus x, and x, and it returns Cpi plus 1 of x squared. So if you want to prove that Cpi plus 1 of x squared is actually correct, you just need Cpi of x, Cpi of minus x, and x. So
What is beta?
beta? Beta was the betas that was randomly sent in the beginning from the verifier. Yeah. So you just need Cpi of x, Cpi of minus x, and x. So this whole thing will continue. So for the second step, if you have Cp1 of x squared and Cp1 of minus x squared, you can now use it to get the value of Cp2 of x raised to 4, and so on and so forth. And at every step, remember the Merkle tree, and remember when we were proving things from the Merkle tree. So if this is your Merkle tree, and you want to prove the value of this element, so this is something like, so you want to prove the value of this element, you would have to give the hash of this element, and you would have to give the hash of this element as well. And using the hash of this element, so element 1, 2, and 3, you can prove that initially what the root was given was actually the correct root. So if the hashes of 2, 1, 2, 3 does not equal to the initial root, then you know something is wrong. What is the property of hashes that actually allows me to do this? Does anybody know? Like, why can't I just randomly give some value?
Hard to find collisions. So
Exactly. So it's hard to find a collision, so it's very hard to find some.
random hash.
Right, exactly. Great. Okay, so what has the prover actually given? The prover has given the trace root, CP root of all CPIs, and then it's given f of x, f of g of x, f of g squared of x, and the path of all of them, so that we can prove the Merkle tree. Cp0 of minus x, Cp0 of plus x, and the path, and so on and so forth until we get to the end. We get a constant polynomial. Okay. So we can actually first show how to make this non-interactive. Okay. So using Fiat-Shamir's protocol, we can make this non-interactive. You have any sort of protocol. This is a three-way protocol. The prover will send some commitment, the verifier will send some query, the prover will send a response, and the verifier will use the commitment to verify the response. And if the verifier is satisfied, then yes, the prover is correct. How do you turn this into a non-interactive
You can introduce
protocol?
middleman,
Middleman. Can you elaborate?
kind of oracle.
Oracle for what?
Initially, the interaction happens between prover and the oracle, and
Mm-hmm.
after that, then the information transfer happens between oracle and the verifier.
Yeah, very close. So can you tell me, like, where is the security coming from in this protocol? The security comes from the fact that the verifier is giving the query. So the query is completely random to the prover. So is there a way we can simulate that sort of randomness using a hash function? Answer is yes. So what this protocol does, and there are many different versions of this, is that the prover has some commitment, and the oracle in this case would be a hash function, the hash function that is publicly known to everybody. So the prover will compute R, which is the hash of C appended with some public information. Then query I would just be the hash of R appended with I. And then Ri is just the response to Qi. And Ri, comma Qi pairs are made publicly available with the commitment. I is the index. So you have some Q1 to Qn queries. Okay. What would be the verifier's protocol for verifying this? So the verifier is given a commitment C, is given the publicly available information, the hash function as well, and the QI-RI pairs.
He can pass the private.
Sorry? You can assume the hash function is a keyless function for now, so it doesn't have any private key. So some verifier, this information is publicly available. Now the verifier wants to actually verify that the prover did everything correctly. So the verifier does is first, the hash function is publicly known to everybody. Public information is also known to everybody. So the verifier will compute R, which is just the hash of the commitment appended with public information. Then it will follow the same process as the prover. It will verify that query Qi is actually obtained by hashing R appended with I. And then using the commitment, it will verify a response for every query.
Where are the queries coming from?
The queries are generated by applying a hash function to R appended by I.
It is
The verifier does not know R, right?
The verifier does know R, right? Because C, the commitment is publicly available. The commitment was broadcasted by the prover, and public information is public by default. So where is the security coming from in this protocol? Does anybody have any idea? Sorry?
The hash function, the queries generated by the hash functions will effectively be random.
Exactly. So because the hash function is collision resistant, well, actually not exactly collision resistant, there is another property in use here. But because effectively the hash function is random, you can assume the prover doesn't know what query I is going to be. The commitment, sorry?
Who sets the commitment?
So the commitment is the roots of the Merkle trees, remember? So the commitment was sent by the prover like beforehand, and in this sort of non-interactive protocol, it's made publicly available to everybody. Any more questions? Okay, great. So we've discussed how to make this protocol non-interactive, but what is exactly the time complexity of the prover and the verifier in this case? Kind of revealed the answer already, but there are log n rows, as you can see, because every time I'm dividing the degree of a polynomial by 2. and I'll at most do that log n times. And for every query, the verifier has to go through the path, and the path itself is log n length long. So essentially, I have log n queries with some log n time complexity per query. So I have log squared n total time complexity for the verifier. What about the prover? Can somebody tell me the time complexity of the prover?
And log.
Right, exactly. So the time complexity of the prover comes from the fact that initially we had to compute the fast Fourier transform of the initial polynomial, and that itself took n log n. But after we're done with that, every subsequent calculation is just O of 1. So that would just be O of n plus O of n by 2 plus O of n by 4 and so on and so forth, which is just O of n. Great. Okay, so that's all, but I just wanted to, I feel like you haven't really understood where the security comes from in this protocol. So why don't we try to break this protocol, and then we can discuss where the security actually is. So what if, so here's what I'll do. Going to remove this. This is the trace. This is CP0, and so on and so forth. Let's say that the prover decides to be a little cheeky and changes the kth element of the trace. And so the Merkle tree itself has changed, right? Because this is not the correct value of, so what was the trace exactly? It was f of not equal to f of some h into gk, I think. Yeah, so, sorry, w. Yeah, so let's assume that the prover decides to change this value. How will the verifier know that this value has been changed? Where in the proof, or where in sort of the commitments, will the verifier find out that something is wrong?
Like the hash of that node will not match.
Sure, the hash will not match. No. So what I'm assuming is that for the trace itself, like the initial root, the initial Merkle tree that was. Sorry?
Was it wrong in the commitment?
Yeah, it was wrong in the commitment only. Yeah, exactly.
Composition polynomial should not. Oh, can you show the slide of composition polynomial? बनेगा फिर.
Which slide you want? QI, RI. This one?
Yes.
Oh no, the last.
The last one.
Yes.
This one? Yeah. So, yeah.
RI is not in, is not hashed, right? Like RI is
response from the query.
is not hashed. Right?
It's not hashed, right? Oh, sorry. Oops.
Like RI.
So there is no problem. Like it will not really reveal any information.
Yeah. RI will not reveal any information. RI will. Well, so this sort of protocol is happening throughout, right? Because you have a lot of queries, right? Remember the three message protocol? There are a lot of these 3 message protocols that are happening throughout. So there are a bunch of QIs and RS for a bunch of different sort of places in the proof. So which place in the proof will tell the verifier that this is wrong and the prover is trying to cheat?
Should not satisfy the polynomial.
So what if CP0 just was the correct polynomial itself. So
CP0 is exactly polynomial is already
So the idea is, if this is wrong, this leads to CP0. And somebody tell me why it leads to CP0? Because the CP0 formula was just a combination of P0, P1 and P2. So if the kth element is wrong, then there is one element in CP0 that is wrong. At least one element in CP0 that is wrong. Okay, fine. Now this element of CP0, remember this, if this is element minus x and this is element x, x and minus x together gave you CP1 of x squared, right?
Different hash stays.
Right, so eventually at some point you'll reach some value that was dependent on this minus x. And when you reach that value, you'll find that, oh no, this doesn't satisfy, because the Merkle tree of this, so the Merkle tree of this will have some root, and it was calculated with respect to the correct value. But you're given, sorry?
changing the composition polynomial on the basis of the values we have,
Right.
and we calculate the Merkle tree from the composition polynomial.
Right. Yeah.
So
Like the wrong Merkle root is compared to what? Which Merkle root? Like whatever we get at the end,
Uh-huh.
the Merkle root
Uh-huh.
is compared to what, to check like if it is correct or not.
It's compared with the initial commitment of this CP of I. So we went through this whole process, right, of sending these betas, creating these polynomials, finding the values of these polynomials, and then committing them in a Merkle
The
tree.
roots that were committed earlier during the work
Connected with the correct value.
Okay. I get your confusion. Yeah. Okay, so let's take. There are two cases here essentially. There is one case where I've changed this value, and it's only really propagated up to some certain level, and then the rest of the values are correct. In that case, you will have some point in the end where this is wrong, right? If it propagates all the way to the end, do you see that CP0 would not satisfy the fact that it's a polynomial? Because will not satisfy the fact that it's a low degree polynomial. So CP0, if I randomly change this value, with very high probability, the polynomial that I would have to interpolate in CP0 of x would be of degree close to 8k. But in actuality, the degree is just k, right? And so this would be caught. So if everything is done correctly, this would be caught by the fact that the number of levels would be more than that are required. Okay. So does everybody understand this?
Basically, if one value change, we won't get a polynomial.
You will get a polynomial.
Sorry.
The degree would be high. Yeah.
Why would the levels increase on just changing a single component? Because the size remains the same, and aren't we still having the size in each step?
Because so you change one component, and you have a polynomial that satisfies all 8k points, right? The polynomial is of degree k. If I randomly gave you 8k points and told you to create a polynomial that satisfies these 8k points, it would be a degree at least 8k. Yeah. So if I randomly change this point, it's essentially like I'm randomly generating 8k points. This is something you'll have to prove. But for now, I'm just asking you to just take it at face value that if I randomly change this one value, it's essentially like I have some random 8k points, and my polynomial that would interpolate those 8k points would be of degree almost 8k.
Okay.
So that would cause issues in the number of steps.
But still, like at any point, even if the values were correct, won't it still take as many steps? Because at every step, isn't it always reducing the size to half, like CP0 to CP1?
We're reducing the degree by half, right?
Degree is reducing by half.
So if the degree is,
There is 3 more steps.
yeah, it would take 3 more steps, exactly.
And like, does taking 3 more steps makes much of a difference?
Right, exactly.
Yes.
That's the point.
And 3 more steps. Yeah.
Mhm. Any more ideas on how to break the security of this? So is there something you don't understand with the security of this whole method? Because if there's something you don't understand, you can think about a way to attack this construction, and then we can discuss on how that attack will not work. That will give you the intuition.
Like, exactly where is this degree thing playing a role? I can't.
Mm-hmm.
Like, if it is of 8k degree,
Mhm.
of 1k degree, how are 3 extra steps? Like, on each step, I'm halving the size only.
Right.
Even if it was of k degree, I still have 8k points in the like trace.
Mm-hmm.
Right.
You will have K.
So I'll have 8k points, but the degree is k. So the number of points will always be greater than equal to degree. Yeah.
How is the number of steps increasing?
So okay, so initially my degree was k, and my number of points was 8k. Right. When I get to the bottom, that is when I have my constant polynomial, the number of steps for this would be log base 2k. Right.
CP will
K is the degree. Right.
Okay, degree. Okay.
I'm reducing the degree by half. But the number of points, the domain, the size of the domain would be 8k divided by 2 raised to log 2 by k. Agreed? Which would not be 1. Right. Okay.
How will the verifier knows this?
How is the verifier knowing what?
What is the query that verifier can give such that he knows this?
Knows the degree of the initial polynomial?
Yeah.
That was given in the problem statement itself, right? So we wanted to, I think it was something like a of I plus 1 is equal to a of I squared plus a of I minus 1 squared. And we wanted to show that a1022 is some specific value, right? So the verifier knows this value. And this value gives us the degree of the polynomial.
And then your byte is near equal and not equal.
Right. So that has to do with the fact that we're randomly choosing these betas. And because we're randomly choosing these betas, there is some like very low probability occurrence that even though this step was wrong, it gets corrected somewhere down the line. That's just for that case.
So there will be like nearly 1 in like 2 power 85 or something that would be off.
Right. And if you're interested, I highly recommend you read the FRI paper. It's pretty dense, but it's very interesting.
Which paper?
FRI. Yeah. Okay, so that was it from my side. Yeah, go ahead.
Can you explain the non-interactive part again? How it is becoming non-interactive?
Yeah, so the interactive, do you understand the interactive part first? Can you explain to me the interactive part?
Like the prover is sending some commitments.
Right.
Like verifier will send some query.
Mm-hmm.
It will like process on the query and send it back.
Sure.
In query will be some random variable.
Right.
And like, is this
done repeatedly? Like, is the commitments also done repeatedly, or
So
just
queries are done repeatedly.
Queries are done-
Commitments are the same always.
commitments are just done once now?
Just once. The roots are sent initially. Yeah. Yeah. So yeah, go on.
So I'm okay with that part.
Yeah.
Like, how is it getting committed in non-interactive?
So the whole fact of the non-interactive part is with a verifier we know that as a verifier, if you're trying to prove if you want to prove from a prover, you're randomly choosing that queue, and you know that because you're randomly choosing the queue, the prover itself has not like chosen a specific queue that benefits him, right? We want that randomness to still be there, but we want this randomness without a verifier. So we get this randomness through a hash function. So
He's providing the hash function.
so this hash function is publicly known. So there are some publicly known hash functions like SHA-256.
Achha,
These are like developed.
what is the role of verifier here?
So the verifier would now have to. So the prover could basically just send anything, right? Any random commitment, any random QI, any random RI. The verifier would actually have to go through and actually check that this response is actually verifying the query, and the query was actually correctly randomly generated through a hash function.
So basically, the prover is sending some commitment.
Sure.
There is hash function publicly available.
Yeah.
He will like process on that hash function,
Mm-hmm.
send the response himself.
The response is not sent. The response is just. You talking about capital R, right? Or yeah, or small r? RI. Yeah, RI is sent. Yeah, my bad.
RA is sent,
Mm-hmm.
and then what is verifier doing?
Here,
There is no verifier.
what is verifier doing exactly?
Yeah. So, okay. Give me a second. By the hash function. So there's like an oracle here. This oracle is your hash function.
So basically, verifier just verifies
The
that
query is
R
nothing but
and-
beta.
Sorry. The query.
Nothing but beta.
So verifier just verifying that R and like beta are matching.
Right. Exactly. Yeah. So the betas themselves would also be generated by a hash function. Yeah. That was your doubt. Sorry, I should have clarified this. Yeah. This is also important.
I still didn't understand where is it being used.
Oh, beta. Oh, okay. So in the sorry. It was in the initial part. Sorry. Yeah. So the new function that we get. So initially we had some polynomial CP0 of x, right? We converted CP0 of x into some even part of x squared plus x into some odd part of x squared.
Okay, that X was replaced with.
Yeah, that is replaced with beta.
That query like what would the beta query?
So this x over here is replaced with beta. And so that this P1 of y would be our new polynomial.
Commitment is the trace route, the starting route.
Commitment is the entire thing. So we are committing at every step of the protocol. We commit at the initial, so we commit the initial trace, right? What do I mean by commit? I create a Merkle tree and I send the root of the Merkle tree to the verifier. So I'm committing on the trace, I'm committing on CP0 of x, committing on CP1 of x, and so on and so forth.
But we will get CP0 and all of these when we send a query.
Why exactly?
Actually, CP2 is but here सारे के Merkle roots को as a form of commitment
अच्छा
भेज
उसमें
दी.
पहले ओ ठीक है.
So one step that is correct is that yes, you need alpha 0, alpha 1, and alpha 2 to get CP0 of x. And initially these are like given by the verifier, but to have randomness, we can just also have some sort of hash function of some known value that gives alpha 0, alpha 1, alpha 2.
Here hash function will generate only one query.
No index के साथ.
Yeah, with an index. Yeah.
Basically, since we're using the commitment done by the approver and using it the to hash, like this puts the part of the security, like
Yeah,
he cannot change the commitment.
exactly. So if you actually go into the security proof of this, that is the very key part, that you're actually using the commitment to
As a part of the hash.
as a part of the hash. Yeah.
Calculus and random index किसका
Could you explain the complexity of part of the security?
The complexity of the
When you like made it m log n from
fast Fourier transform. Yeah. Okay. So we'll do an induction type proof. So like my proof essentially is
state first what we wanted to calculate. What are the values at which we wanted to calculate f of x?
yeah. So we wanted to calculate f of x at the m roots of unity.
And since it is of degree n, it would using a knife process it would take m into n.
Mn, right.
But we are doing
But
efficiently.
we can do it in m log n complexity. And the way is, suppose I have a polynomial of degree n, and I want to compute it. So, okay. So you guys have all done call 106? Doing. Okay. Yeah. So, you might have seen these types of relationships. So if T of n is the time complexity for a degree n polynomial, this is equal to the time complexity of an n by 2 polynomial twice. Because remember, we're calculating it for the odd and even polynomial. So this is twice of n by 2 plus O of n to actually go back and calculate the values of the mth roots of unity. So you get this sort of recurrence relation. And if you solve this recurrence relation, this is O of m, sorry. If you solve this recurrence relation, you get T of n is O of n m log n. So that's how that comes. So it's a divide and conquer type proof. Have you guys gone through merge sort? So essentially like merge sort, we divide it in half, we compute it on each of the halves, and then we merge the solution together. Any more questions? Okay, so that's pretty much all from my side. Now Arnav will discuss the hands-on part, where I guess you'll get a little bit more idea on how it all works.